In this lecture, we will be discussing Lagrange interpolation, or better say a much basic part, that is my linear Lagrange interpolation. But before starting this topic, let me show you something. If you can remember that if we are having two data points, or better say two coordinates, let's say x1, y1 and x2, y2, we will always be having a straight line that is passing through these 2 points x1, y1 and x2, y2. Similarly, if we are giving 3 points, let's say x1, y1, x2, y2 and x3, y3. We will always be having a parabola that passes through all 3 points, or better say a quadratic equation. That is what we can observe here is, if we are having two data points, then we need a polynomial of degree 1 such that the polynomial passes through both data points. And suppose we are having three data points, then we need a polynomial of degree 2, that is my quadratic equation. Or more generally we can say, if we are having n data point or n coordinate, then for this we need a polynomial of degree n minus 1 which passes through all these points, right? Okay, let me take an example here. Suppose I am having three data points, minus 1 comma 6, 0 comma 6 and third one that is 1 comma 8. Obviously you can tell that there will be a quadratic equation which passes through all these 3 points. Let's assume my equation to be y is equal to ax squared plus bx plus c. Putting these values, will be having three linear equations in three variable. So 6 this will be equal to a minus b plus c, this 6 that will be equal to c, and this 8 that will be equal to a plus b plus c. Solving these three simultaneous linear equations will get a is equal to 1, b equal to 1 and c is equal to 6. So actually this was nothing but this curve y is equal to x squared plus x plus 6. Okay, now what we can do is we can write this polynomial in a bit different way. How we can write it as? We can write it as some variable, some constant a, x minus minus 1 into x minus 0 plus b, x minus 0 into x minus 1 and plus c multiplied by x minus 1 and x minus minus 1. Okay, here I choose minus 1, 0 and 1, which are nothing but the x coordinate of these data points, right? So what we can write it as, y is equal to a into x squared plus x plus b into x squared minus x plus c into x squared minus 1. And this is nothing but x squared plus x plus 6. Solving, what we'll get is a that is equal to 3, b that is equal to 4 and c that is equal to minus 6. That means we can write a polynomial in this form. Okay, what I actually wish to say is, if we are giving these three data points x0 comma y0, x1 comma y1 and this x2 comma y2, then we can always write a second degree equation in this form. Y is equal to a naught x minus x1 into x minus x2 plus a1 x minus x2 into x minus x0 and the last term that is plus a2 x minus x0 into x minus x1. Okay, you can observe this thing as well, that these three terms are there only, x0, x1, x2 and this three written in cyclic manner. Like this first term x1, x2, in second term we are having this x2 and x0, and in this third term we are having x0 and x1. Okay, so you can write a more general formula if you are given some n data points, but here our case is limited to linear interpolation only. So for our case, what is relevant is, we will be having only two data points, that is x0 comma x1, x0 comma y0, and second data point that is my x1 comma y1. So linear interpolated formula, that would be y is equal to a naught into x minus x1 plus a1 into x minus a naught. Now what we are having is, for x is equal to x naught, the corresponding value of y is equal to y naught. So from this we can write as y naught, this is equal to a naught into x naught minus x1 plus a1. Obviously this term will vanish to 0. So from here what we can get is a naught is equal to y naught upon x naught minus x1, and similarly when we will place x is equal to x1 and y is equal to y1, you will get a1 this is equal to y1 upon x1 minus x0. So let me rewrite my formula as y is equal to y0 upon x0 minus x1 into x minus x1 plus y1 upon x minus x0 into x minus x0. So this is nothing but my formula for linear Lagrange interpolation, and this way we derive this. Okay, rewrite this again as y0 into x minus x1 upon x0 minus x1 plus y1 into x minus x0 upon x1 minus x0. So this is my linear Lagrange interpolation formula, and these two terms, this term and this term, they both are called Lagrange basis polynomial. Okay, and let me represent it as L1, and let's say this is L2. So what you can observe, the sum of this L1 and L2, what is that? So my L1 plus L2, this is nothing but 1 only. For the proof of linear Lagrange interpolation. Okay, now let me make you show the another aspect what you might have read in your class. So suppose we are having an equation y is equal to ax plus b. This is my linear equation, and what we are given is this passes through x naught comma y naught, x1 comma y1, and the most general case, that is some point x comma y. Now this point and this point, that means all these 3 points will satisfy this equation. And if this with 3 equations will satisfy this means this point, let's say first point, my second point, and this is my third point. So this 3 points, they will be linearly dependent. If you remember sub concept of your linear algebra, so this 3 points, this will be linearly dependent. And as they are linearly independent, we can write as determinant of this matrix yx1, y1x11, and y0x01. This will be equal to 0, and when we will expand this determinant, this will write x1 into 1 minus x0 into 1 minus y1, and corresponding to this we will be having x into 1 minus x0 into 1, that would be x minus x0, and plus y0, and corresponding to this we will be having x minus x1. So this will be equal to 0, and when you will rearrange all this equation and try to find the value of y, this will come as this Lagrange linear interpolation formula only. Okay, let's move on to graph now. Suppose this is my equation of sin x. As remarked earlier, what we do in a interpolation is we try to approximate this equation of mine with some polynomial. Here in this case, our polynomial is nothing but a linear equation. And obviously, if we are approximating this equation with some linear equation, there will be some error. And like at this value of x, we are having this much error. At this value of x, we are having this much error. And at this value of x, we are having this much error. Now question arises, how can we approximate this error, or how can we have a bound to the error that this will be my maximum error, my error will lie in this particular interval. And for that we do have a formula. Okay, let me make you show the formula. Actually the most general formula for error bound, that is this fn plus 1x, that is n plus 1 derivative of fx upon n plus 1 factorial into x minus x naught, x minus x1 up to this term x minus xn. Here in this case of ours, we do have a linear equation that is the value of n is equal to 1. So this will be f2x upon 2 factorial into x minus x naught into x minus x1. f2 of x, that is second derivative of fx, or we can write it as f double dash x upon 2 into x minus x naught into x minus x1. Okay, if you want to prove this formula, you can refer the first lecture of mine, that was Introduction to Interpolation. There I have explained in detail how to prove that this is my maximum error bound. So this was all about today's lecture, Lagrange linear interpolation. Okay, in the next lecture we will we will discuss the most general case of Lagrange interpolation, and in the next lecture we will discuss a problem based on linear interpolation, linear Lagrange interpolation, and a more general case. Thank you so much. Stay tuned.